start off with a little bit about me because I'm not that important. While people are still talking, it's fine. So my name is Yujian. I have a AI ML background. I've been working in this field for maybe like 10 years. I started at IBM as a software engineering intern when I was 16. I did some research on machine learning and published some papers. And then I went to Amazon where I worked on AutoML. And then I went into natural language processing, and here we are at Zilliz working on the cutting edge of what's going on with large language models. Then let's cover who Zilliz is. You may have heard of Milvus or GPT Cache. These are both very popular projects of ours. Zilliz is the company that maintains these projects. We were founded in 2017. We're based in Redwood Shores, California. So we're out on the West Coast. If you are ever out there, come say hi. I flew in last night at 1 a.m. So now let's get into the actual meat of the talk. It seems like most people have kind of settled down, so I can start actually talking. So why do you need a vector database? How do vector databases help? How do you evaluate a vector solution? And then some tips for getting started. This is what we're going to cover today. So I'm going to start with, why do you need a vector database? Okay, so vector databases are the solution for handling unstructured data. And unstructured data is everywhere. Okay, here we go. This is working again. So unstructured data is all around us, and a lot of numbers float out there around how much it really is. And there's this trope of 80% of data is unstructured data, and 90% of that data is not analyzed. So it's not used right now. So how do you use that data? You use it in vectors. And you can really use this with any kind of data, text, audio, images, videos, whatever you want. All right, guys, so we're going to talk about some common AI use cases. These are some use cases you can see up on the screen, but the main idea I want you to get from this slide is vector databases are critical to similarity search and pretty much the only existing solution. And then I'm going to go to the next slide where I'm going to highlight the one thing that you guys probably want to hear about the most: large language model, augmented retrieval, retrieval augmented generation. This is also the most popular case for vector databases. Okay. So the reason why large language models need vector databases is because they hallucinate. You guys have probably seen this in the news by now. There's a lot of news around ChatGPT and what's been going on with it. And recently we've seen some pretty crazy things, like a lawyer using ChatGPT and getting in a lot of trouble. And you don't want to be that guy. And you also don't want to be the guy who says that like France gifted Lithuania the Vilnius Tower in 1980, because that's not true. So the reason why large language models have these issues is because they're neural networks. And this right here, this example, is an image of what GPT's architecture looks like. GPT is a decoder-only architecture. And what that means is that it takes a set of state encodings, and it transforms that and predicts the next token or word out of these encodings. So for example, the image shows that the chicken walked across is the input, and then the output is the prediction from ChatGPT or GPT, whatever, and it says across the road. So this is essentially how GPT works. And so an example use case in real life of using this with large language models is you essentially have some documents. If you are working at a corporation, if you're working at enterprise scale, you probably have hundreds of thousands, millions of documents, and you want to be able to query these documents, right? I mean, I don't know if you guys saw the research back in the 2000s that showed the average knowledge worker takes almost 2 hours a day to query these documents. And so it's much, much more efficient to use something like a large language model. And in this case, we have actually built an example of this called OSS Chat. And you can check it out at osschat.io, and it allows you to chat with open source software. And if you have an open source project that you want to submit, you can go to our site and submit it. Okay, so the way that this LLM hallucination is prevented is basically by inserting your data on top of the large language model, right? So you have your large language model as your underlying compute, and then for you to be able to access your documents, you have to add a layer on top, and this is going to be a data injection layer. And this is where you put your data so that you can, first the query comes, and it goes to the vector database on this data injection layer, and it gets that information, and it uses the large language model to then send that back to you in a human readable format, okay? So you can use vector databases to build on your data, to eliminate hallucinations, and to solve customer problems with AI. So the takeaway I want you to get from this is vector databases are a critical component for building AI applications on top of your data. And I also have a question for you guys. What was one of the 3 things that I said you could do with vector databases in the last slide? Somebody raise their hand. Okay, yes. Oh, nice, thank you. That's a great answer. You are correct. You get a sock, sir. Oops, sorry, that I missed. All right, I'm gonna switch spots now because I'm gonna go to the next section. All right, how do vector databases help? Let's cover this. Where do vectors come from? What is a vector, right? So you have your knowledge base, some set of documents, some images, some videos, whatever. And what you do with that is you put that into a deep learning model or an embeddings model, and it spits out some vectors, and you store your vectors in a vector database such as Zilliz or Milvus. So vectors are the internal representation from a machine learning model of what that input data is. So vectors really help us with this thing called semantic similarity, and I'm gonna cover this here so that you have an idea of what semantic similarity is. I want you to keep in mind that this is just a very toy example. You will never see 2-dimensional vectors in real life, and you will never see people compare them with Euclidean, not Euclidean distance, Manhattan distance. So in this example, we have 4 words. We have queen, woman, man, and king, and we have a bunch of numbers that go with them. And so what I want to draw your attention to a few things. First, I want to draw your attention to the first dimension, where you can see that queen and woman and king and man have the same value along the first dimension. This tells us that these words mean the same thing along that dimension. The other thing I want to draw your attention to is that queen and king and woman and man have the same difference along the second dimension, and that means that these words have the same relationship along that dimension. And in the, equation that I have over to the side there, you can see what I've shown is that if you take the vector embedding of queen, 0.3, 0.9, and you subtract the vector embedding of woman, 0.3, 0.4, you get 0, 0.5, which probably means something like royalty. And if you add the vector embedding of man, which is 0.5, 0.2, you get 0.5, 0.7, which corresponds directly to the word king. The main thing that I want you to take away from this slide is that vector embeddings allow you to do math on things that are not originally numbers, okay? So, for example, this is 3 sentences. How did your company increase its bottom line? How did your company make more profit? How did your company increase profitability? These are 3 sentences that everybody cares about and all mean the same thing. However, if you were to do keyword search, or if you were to do fuzzy search, you would not be able to find these sentences if you did not phrase it correctly. So vector search, right, with the similarity that we just saw earlier, vector search allows you to use numbers to represent these sentences so that when you do your search, you will get all 3 sentences back. Okay, and there's more. It's not just text. It's also images. So for example, let's say you think you look like Taylor Swift. What you could do is you could have a vector database full of vectorized images of your favorite celebrities. It doesn't have to be Taylor Swift, she's mine. But you have your vector database and you put your image in there, and then you say, return to me the one that looks the most similar, the closest. And that is another use case. So text, images, audio, and more. So vector databases are purpose-built to handle vector embeddings and perform similarity search. And the takeaway here is, if you need to find semantically similar data, you need a vector database, okay? There's another question coming, and it's gonna come with a sock. Which one of these is not Taylor Swift? Who said the second one? Here, you can. Thank you, thank you. That was too easy. How do you evaluate a vector database? Okay, so this is where I'm going to plug Zilliz/Milvis. This is the company that I work at, right? We are purpose-built to store, index, and query vector embeddings from unstructured data at scale. So the at scale, the little bold part that I have written over there, that is the thing that we are the niche at. You really start to see performance differences once you hit 1 million or 10 million vectors. And there's this open source library called VectorDB Bench that you can go check out that will show you these things. And I'm not going to read everything on the screen, so you should take a picture if you want to remember this kind of stuff. But I'm going to go over it again in the next 2 slides, okay? So why would you not use a SQL database or a NoSQL database, right? These are something that everybody's familiar with. So let's start with the idea of what does a SQL database or a NoSQL database do? When you are performing search on a SQL database or a NoSQL database, you are essentially asking it to do a key value comparison, an exact match. You say, here's my key, find me something that has the same key. Whereas with vectors, you're actually looking for approximately similar data. And not only that, but you're looking for this not with a key, but with a series, a very long series, often hundreds of numbers. So every time you do a query with a vector database, you need to be performing thousands, tens of thousands, perhaps even hundreds of thousands of calculations. Without a purpose-built infrastructure, your SQL database could be sitting there spinning for, I don't know, like 8 days before you get a result. And so that's why you would need a purpose-built infrastructure of a vector database, right? The takeaway here is that vector operations are too computationally intensive for traditional database infrastructures. So what about a vector search library? I've actually talked to quite a few people here who have heard of FACE and who have heard of HNSW. These are common vector search libraries now. The reason why you don't want to use a vector, I'm also not going to read all the sentences on this slide, by the way. The reason why you wouldn't want to use just a vector search library is that it doesn't come with the infrastructure that you need, right? Similar to how SQL databases lack this ability to perform many, many calculations, vector search libraries lack this ability to give you backup, to give you multi-tenancy, to give you reliability, and all of these other things that you would need with a database. So the takeaway from here is basically vector search libraries lack the infrastructure to help you scale, deploy, and manage your applications in production. So the takeaway from this entire section so far, vector databases are purpose-built to handle indexing, storing, and querying vector data. Milvis and Zilliz are specifically designed for high performance and billion-plus scale use cases. So I have another question for the crowd. Why would I not use a SQL database? Woo! This guy knows what's up. There's 2 more socks. Tips for getting started. So here's some links you can use to get started. I know this is a very quick talk, so there's some time for some questions, but essentially there's a benchmarking tool. You can also find the benchmarking tool on GitHub if you search up VectorDB Bench. And what this will allow you to do is to benchmark on your own data. You can download the open source, and it'll create a bunch of graphs for you that show you like queries per second, queries per dollar, throughput, latency, all that kind of stuff. We also have a Vector Database 101 series. So if you go to zilliz.com/learn, you can find a bunch of vector database stuff on there. And recently, we also have a bunch of like LLM RAG app tutorials. This is pretty recent for us, but this is essentially all that I work on. So if you have questions about retrieval augmented generation, I'm your guy. And if you want to get started, we have 2 options for you that you can get started for free. One is Milvis open source. We have an open source repo that's very popular, 23,000 stars, some 5.6 million Docker pulls, etc., 300 contributors, something like that. And then Zilliz Cloud, which is a SaaS fully managed version. You can get started. If you have OpenAI embeddings, we'll support up to $250,000 for free. If you have embeddings from Hugging Face, you can probably get some more in there. So yeah, start building with Zilliz Cloud today at zilliz.com/cloud. And if you have any questions, I have 2 socks for the first 2 people that ask questions. And no, your question cannot be, can I get a sock?
Input to you to the headset.
Yeah,
That one doesn't have as much,
but it's the same one. It's just
Are you asking like at what scale?
I was going to say, whenever you point to wireless mic, just
Oh, how many? Oh, what does a vector embedding look like for a photo? Oh, okay. So a vector embedding, I'm gonna throw this sock out to you. So vector embeddings are gonna. Sorry, that was a really bad throw. Wow. Okay, this is why I don't play basketball. So vector embeddings, it's gonna differ on the model that you use, and some models have. So for example, ResNet 50 has 2048 dimensions on it, and OpenAI's embeddings have 1536 dimensions on them. And if you go to Hugging Face, there's a couple really popular models. So there's one called MPNet5. That one has 768 embeddings. And there's another one called Mini LM. L6 and L12 both have 384 embeddings. So depending on the embeddings model you use, your vector data is going to have different dimensionality. Yes, sir. I'm sorry? Will it work? Yes. It depending on what's your use case. Oh, I'm so sorry. Wow. I mean, you could. Yes. That is 100% a possible use case. That is a very interesting use case. Okay. Yes. I have no more socks, but I believe I have a few more minutes for questions. If you have more questions, you can stop by our booth downstairs. We are right by the center stage entrance and also right when you walk in. So, yeah. Yes. Sure.
Is there a way to combine 2 different for say similarity search paths? So you may third separate model. As a one model in audio, one those are tertiary copies,
Right. So the question is about whether if you have 2 different indices, can you use a third model to compare them? So vector embeddings can only be compared if they're the same dimension. So, huh? Let's say they are. Then yes, sure, why not? But I also I think that the better solution to that would be to just use a multimodal model that already exists. That way you can say, here's this image, you can get the text embeddings, you can also get the image embeddings out of it. Then you can have, then you're working with the same model, and so you have more consistency across time. Now, there are some use cases where you want to use different models. There's this specific use case for measuring machine learning model performance over time called graceful degradation, and that is the most prominent use case for using different models that I see. Yes, sir. The question is about whether or not there are probabilities behind the words. So vector embeddings are derived from a machine learning model. These are not defined by us. So the probability, it depends on your model. It depends on the data that you give your model. Any other questions? No. Okay, cool. Thank you guys all for coming.